All right, good morning, lads and ladies. Welcome back to the wonderful world of calculus. Please forgive the mess that you see around my room here. We're in the process of moving, which means things are going to be a little messy, but that's all right. Today, we have a couple really cool things to talk about, namely derivatives of trig functions. And if there's time, we'll get to the chain rule, but we'll probably spend most of the day on derivatives of trig functions. So trigonometric functions form a very important family of functions, some of the most important examples in all of calculus for many, many, many reasons. And it is exciting that we'll finally be able to start working with them in this setting. So let's get into it. I know I'm excited. There we go. All right. Today is the 1st of February, 2021. And today we are talking about trig derivatives, which is section 3.3. And if we happen to get through all of these, then we will talk about the chain rule. Which is section 3.4. This one's maybe, if there's time. I think it's not a bad idea to remind us, kind of a little bit what the trig functions look like. I know there's a lot of times details can be forgotten. So let's start with the basic stuff. Do a quick trig refresh. All of our trigonometric functions are defined using the unit circle. So this is the x direction, this is the y direction, this is the unit circle. And if you subtend an angle theta, right, whatever, if you start along the positive x-axis, as we always do, and you rotate up theta along the unit circle, the equation of the unit circle, by the way, is x squared plus y squared equals 1. That's the normal Cartesian equation for the unit circle. If you remember your conics from pre-calculus, the unit circle is, of course, a conic section. And this is the equation for a circle whose center is 0, 0, and whose radius is 1. That is the unit circle. So if you start along the unit circle here, you rotate up theta radians. We always, always, always use radians, no degrees. Then the point here will be cos theta, comma, sine theta. In other words, the x value along the unit circle is cosine, and the y value along the unit circle is sine. So this is that y value right here. So this length here is sine, and this length here is cosine. But the things you need to remember, at least when we're first starting off, is that, yeah, the x value along the unit circle is cosine, the y value along the unit circle is sine, and then you rotate theta, always measured in radians, always from the positive x-axis like this. The fact that the unit circle has this equation and that the x value is cosine and the y value is sine gives way to the first Pythagorean identity. which is just that cos squared theta plus sine squared theta is always 1, no matter what theta is, no matter what you have inside the trig functions, as long as it's the same thing inside both. I'm not going to remind you the particular values of the unit circle. This is something you need to know. So let's say here, you must know the values along the unit circle. At, theta equals 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, and so on, right? You got to know all those values. Got to. If you learn them for trig and forgot them since, then it's time to relearn them. Absolutely no room to not know these things. I do have some resources up in the modules if you're worried about this. There are tricks for memorizing the angles in radians, and there are tricks for memorizing the points, the cosine values and sine values. But you must know these. You must know this. And what other things? So we should talk about the graphs a little bit. If you take this spinning circle, and as you spin around, you just trace the y values, then as that spins, it goes up, and as it spins more, it comes back down and goes back up. That will give you the graph of the sine function. So I'm going to label this as my theta axis. I'll label this as 1 up here. I'll label this as -1 down here. And we'll call this out here 2 pi. Why not? If that's 2 pi, then halfway there is pi. A quarter of the way there is pi over 4. Oh, sorry, pi over 2. Sorry. And 3/4 of the way there is 3 pi over 2. So all the trig functions are periodic, or sorry, sine and cosine are periodic with period 2 pi. I will draw sine in here and purple. Sine, we know the sine of 0 is 0, because if you rotate up not at all, your y value is 0. The sine of pi over 2, which is the north pole here, should be 1. The sine of pi is 0 again. The sine of 3 pi over 2 is -1, and the sine of 2 pi is 0 again. So should have something like this for the sine function. Easy peasy way to graph sine, right? Just plot the quarter periods. Just throw in a few points, quarter periods, and then connect them. So this is sine theta in purple. And then down here, over here, I'll graph the cosine function. I'll graph him in orange. So cosine of 0 is 1. If I don't rotate at all, the x value is out here at 1. Cosine of pi over 2 is 0. If I rotate up to the north pole, my x value there is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0 again, and the cosine of 2 pi is +1. So this guy should look something like this. And it does. So here in orange, this is the cosine function. Sorry for this little wobble here. Oh, sorry, this pen just wants to go there. All right. So here is the cosine function. All right, hopefully this is review for everybody, right? We're all familiar with these ideas. Sine is the y value along the unit circle. Cosine is the x value along the unit circle. These are both periodic functions with period 2 pi. And if you graph them, they're both these waves that are periodic, again, period 2 pi, amplitude 1. They're 90 degrees or pi over 2 radians out of phase with each other. So if you were to shift this guy to the right, shift the orange guy to the right by pi over 2, you would get the purple guy. Or equivalently, if you shift the purple guy to the left by pi over 2, you get the orange guy. This is your crash course in trigonometry. There's way more than this that you guys need to know, but I don't have time to go through a whole trig course here. So if there are things that you need to refresh, especially values along the unit circle, I can't emphasize enough that you must know these. You must know your Pythagorean identities. What other things are going to get you in trouble if you don't know them? Here, you got another graphs. Oh yeah, the definitions are reciprocal identities. So let me say one more thing here. I'll hold here just for a second if anybody's writing anything down, or if you want to take a screenshot. I'm going to turn the page in about 5 seconds. Okay, here we go. So other things, absolute must-knows from trigonometry are the definitions, right? Definitions of the trig functions. Sine and cosine are defined by the unit circle. The other trig functions are tangent of theta, and the tangent of theta is the sine of theta over the cosine of theta, secant theta, which is the reciprocal of cosine theta, cosecant theta, which is the reciprocal of sine theta, and cotangent theta, which could be thought of as cosine over sine, or if you want, as the reciprocal of tangent. Okay, so these we must know. The period for sine and cosine are 2 pi. The period for tangent is pi. Period for secant is 2 pi. Period for cosecant is 2 pi, and the period for cotangent is pi. Of course, these are undefined anywhere their bottom is 0, so the tangent function is undefined where cos theta equals 0. I'll sketch a quick graph of tangent. So here I'll put pi over 2. Here is negative pi over 2. And here is what tangent theta looks like, more or less. He does this business. And he repeats, right? So his period is pi, and he repeats often like this. So this would be over here. This would be negative 3 pi over 2. And he'll have another branch in here that does the same sort of thing. And so on, on and on and on forever like this. Secant theta also blows up at odd multiples of pi over 2, negative pi over 2, positive pi over 2. But in between, he has these kind of bowl-shaped things. These aren't parabolas, but I hear students call them that a lot. If that helps you remember what they look like, I won't chastise you for it, but certainly they don't fit the definition of a parabola. Over here, again, doing the same sort of behavior. Over here, same sort of thing. Run out of paper there. All right, so the secant of 0 is 1. The secant of pi is -1. The secant of negative pi is also -1, like this. All right, so these are the graphs of your basic trig functions, or at least quick sketches. Hopefully you guys remember all of this stuff, and this is just a rapid refresher for you. The tangent function does more of the same here. So yeah, if you need more trig refresher, please look at the modules, right? In that review materials section on the modules, I have lots and lots of stuff. Graphs, inverse trig functions, solving trig equations, finding domains, all that stuff. And you need to be good at all that stuff. I can hold here for a second. And now we're going to talk about derivatives, right? So we're going to take the sine function and we're going to plug it into that definition of the derivative, and we're going to see what we get. It's going to require some very clever stuff, and I'll show you how we get there. It's not too bad, and there will be a few steps there where I ask you to kind of take my word for something because the geometric arguments are a little bit gnarly, but I'll walk you through them. You ready? Okay, here we go. Okay. Derivatives of trig functions. This is section 3.3. So let's start with, I'm going to use the variable x here. F of x equals sine of x. But with the understanding that x here is playing the role that theta does in the definitions. Then f primed of x is, I don't have any tool to differentiate sine x, right? This isn't a product, this isn't a quotient, it definitely isn't a power function. So the only way I could even start trying to write down the derivative of this thing would be with the limit definition. We got to go all the way back there. So all the stuff that we used last week, power rule, product rule, quotient rule, really doesn't help here. So we have to go back to the limit definition. That is limit h to 0, f of x plus h minus f of x all over h. And I plug in for the sine function, right? What is f of x plus h? What is f of x? Well, if f of x is sine x, then f of x plus h is the sine of x plus h, like this, right? And f of x is the sine of x. And although we might hope that this simplifies in some nice obvious way, you remember from your trig class that it doesn't. There's a fairly complicated identity for expanding things like sine of a plus b. And it's precisely that identity we're going to have to use. So, what is the sine of x plus h? Well, in your trig class, you learned a formula for the sine of a plus b. This was the sine of a times the cos of b plus the cos of a times the sine of b. So the sine of x plus h is going to be sine x times cos h plus cos x times sine of h. All right, just plugging in a for x for a and h for b. So we tuck this into our pocket. And we say that according to this, the line above is equal to lim h to 0 sine x plus h, which is sine x cos h plus cos x sine h minus sine x. Everything's still divided by h. Gucci so far? So this right here, this whole thing in blue is the sine of x plus h, expanded using the addition formula for sine. This is not the same as sine x plus sine h, or sine of x plus h on the outside of the parentheses. There's no other way to get this h out. This is the only way to expand this. Anything else is not correct. It doesn't at a glance appear to be making this limit easier, but trust me, it will. Remember, our goal is to plug in 0 for h. So the problem is that there's this h down here. He's making life hard. And also, if we plugged in 0 for h, the top would be 0. So right now we're in a bit of a pickle. And this identity hasn't fixed that for us yet, but it's going to. I'm going to group some terms together. I'll call this term 1, I'll call this term 2, and I'll call this term 3. I'm going to group terms 1 and 3 together. And then I'm going to split up. So what is that going to look like? This is going to be lim h to 0 terms 1 and 3. So this is going to be sine x times cos h minus sine x. And then I still have my plus cos h, cos x times sine h. And I'm going to give this its own fraction, and I'm going to give this its own fraction. And I'm going to give this its own limit. So I put these two together, so these two over h, that's one limit. And I put this guy together. This guy gets his own limit. So this guy goes here, right? This is 2.
Will it always be term 1 and 3, or is there like a specific reason you did it for this one?
There is a specific reason I did it this way for this guy. Yeah. So this is terms 1 and 3. This is term 2. The reason I'm doing this is because I can factor a sine x out from here, right? These two pieces both have the common factor of sine x. And this piece is kind of what's left over when you group the pieces that have sine x in them and factor it out. So this is going to be lim h to 0 cos h minus 1 times sine of x all over h. And then here I have plus lim h to 0. I'll just leave this. This is, I'll write it like this. I'll write it as sine h over h times cos x, like that. Because what I'm interested in here is sending h to 0. I'm trying to get the x pieces out. So this becomes lim h to 0 cos h minus 1 over h times sine x plus lim h to 0 sine h over h times cos x. And I intend to come in here and deal with these two limits carefully.
For cosine h minus 1, that was an identity you plugged in, right?
Not quite. 1 minus cos squared would be sine squared. Cos squared minus 1 would be negative sine squared. There is an identity that we can kind of make show up here if we're a little bit clever. For now, let me call this one L1, and let me call this one L2. It's actually L2 that I'm going to start with. I claim that L1, so here I'll say a claim. I claim that L1 is 0 and that L2 is 1. And that I'm actually going to get L1 as 0 as a consequence of L2 being 1.
Okay, I'm just like a little confused how you got cosine h minus 1. How do you know to put that in? How did you get minus 1?
If you look at this term right here, right? And you factor out the sign, then this piece would become cos h, and this piece would become minus 1. If I redistribute this sign across these parentheses, I'll have sine x times cos h minus sine x times 1.
Okay, yeah, that makes a lot more sense. Thank you.
That's all right. Yeah. It's a common thing. So when you factor something out from here, and it's like there's nothing left, what's left is really a 1, right? It's not a 0. So,
yeah, I didn't see that. Yeah, I see that now. Yeah, thanks.
Okay. So I want to convince you that this second limit is equal to 1. And there's a handful of ways to do this. The traditional way to do this is using a geometric argument and the squeeze theorem. I'm going to show you that argument, but first, I think I can convince you that that limit is 1 much faster and in a way that you will trust a lot more using Desmos. So I'm going to show you using Desmos that this limit is 1, and then I'll show you the sort of classical proof. Everybody ready? We understand what we're going to do? We took our definition of the derivative, we plugged in the sine function, it blew up to this. We grouped some terms, factored out some pieces, and that left us with 2 limits, this limit and this limit that I need to figure out. If this limit is 0, then this term goes away. And if this limit is 1, then this just becomes 0 times sine x plus 1 times cos x. So the derivative of sine would be cosine, which you may know from elsewhere is the case. But let me see if I can convince you that this limit is 1. Here we go. Here's the function sine h over h. Rescale my axes. All right, so here is sine h over h. And as I get closer and closer and closer to h being 0, this y value is getting closer and closer to up here. Right, we're actually undefined at 0 because sine of 0 over 0 is just 0 over 0. But you see, look at this graph. We've got a hole up here. Where's the hole? It's at 1, right? Look at this graph. Imagine you're walking from the left or from the right towards this hole. What's your y value getting closer and closer to? Clearly, it's getting closer and closer to 1, right? No question. No question at all here. From the graph, the limit has to be 1. So this limit really is 1. And you can think of it as coming from the graph. Or, and here's the classical argument, it is considerably more complicated. But it's worth taking a look at.
Are we gonna have to prove that in the test?
No, sir. No, the derivative of sine and the derivative of cosine are not things I can ask you to prove on the test. So here they are walking through the same process we did, right? F of x plus h, sine of x plus sine of x plus h minus sine x. Split it up, group the terms, and now you've got these limits, right? We need to deal with this limit, and we need to deal with this limit. And they say, as we did, that you know, we've got a challenge here. So what we need to look at is this. They're writing it in terms of thetas instead of h's. That's fine. This is the standard argument. Actually, this is a slightly different argument than the standard one, but they're all geometric. If you look at your unit circle over here, this figure, the blue along this figure is from the unit circle. And they are going to compare some different lengths or different areas. Usually I do this with areas. And triangle theta, BC is from, so they're going to do it with lengths. They say the length from B to C, which is right here, is smaller than the length from A to B. Why is that true?
Because the hypotenuse is always the longest part of the triangle.
That's true, yeah, the hypotenuse is always the longest part, right? And if you look at this triangle, the triangle BCA, the length BA is the hypotenuse of that little triangle. So AB has to be bigger than BC. Now, what is the length BC? Remember again, this blue is your unit circle. We've rotated up theta radians. This is the y value along your unit circle. So the length BC is sine theta. All right, let's look back at our trig thing here. If this point right here is x comma y, then this is the y, which is sine theta. So that length BC is sine theta. The length BA, they say, is clearly smaller than the arc. That's the blue length here from B to A. So they say sine theta is less than theta because BC is smaller than BA is smaller than the blue arc from B to A. That's because a straight line is the shortest distance between any 2 points. So the straight black line BA is itself smaller than the blue arc from B to A. And the blue arc from B to A is theta, right? That's how radians are defined. So sine theta is smaller than theta everywhere within quadrant 1. If you divide through this expression by theta, you get sine theta over theta is smaller than 1. This is one of the inequalities we're going to need to make this go. But here you can see, if sine theta over theta is always smaller than 1, then the limit as theta goes to 0 of sine theta over theta would always be smaller than 1. Now they engage in a similar thing here. So they say, look at the tangent lines at A, which is down here. So this is the red line. The line AD is a tangent line at A. And the tangent line at B, which is this red line right here, the line BE, intersect at the point E. You see from the figure that the circumference of the circle is smaller than the length of the circumscribed polygon. So the red polygon definitely has more length as you walk around it, the perimeter, than the circle inside, right? It just encloses more space, so it's got to have a larger perimeter. You can make all sorts of arguments to claim that the blue arc in here is smaller than the red arcs all added up. So the arc from A to B, which is again, this little blue arc here, is smaller than the piece from here to here plus the piece from here to here, which is AE and EB. So what is AE and what is ED? Sorry, what is AE and what is EB? We're going to build up some more inequalities. They say AE right here is itself smaller than AD. That's evidently true, right? AD is in the same direction, just goes past that. And even if you were to add that to ED, that's no larger than AD. So this plus this is no larger than this. And that you can write in terms of the tangent of theta, right? Tangent is opposite over, opposite over adjacent. So that would be AD over OA. So tan theta is AD over OA, which means AD is OA tan theta. But what is the length from O to A? We're on the unit circle. This is a radius, so this is 1. So OA tan theta is just tan theta. So you get this collection of inequalities. Theta is smaller than tangent theta, and sine theta over theta is smaller than 1. If you string these together, theta is smaller than tan theta, and you know that then you can multiply everywhere here by cos theta, so you get cos theta is less than sine theta over theta is less than 1. Then you use the squeeze theorem. This is not my favorite proof. And if you look in the modules again, I have a slightly easier to follow geometric proof. But for my money, this is good, right? This is the easiest way to see that that limit is 1. We've got technology, let's use it, right? As I get closer and closer to 0, sine h over h definitely gets closer and closer to 1. All this shit here was just to prove that this limit is 1. So let's come back to our argument. For geometric argument. Either way, I'm hoping that you believe me that this limit now is 1. We now know that the limit as h goes to 0 of sine h over h is equal to 1. And it remains to be shown, or we still need to show, or I should say to find, as h goes to 0 of cos h minus 1 over h. So here's how we're going to do this. I'm going to use a trig identity together with the fact that sine h over h goes to 1 as h goes to 0. What trig identity? Well, first I multiply kind of by a conjugate here. I'm going to multiply by cos h plus 1 over cos h plus 1. It's a sneaky trick. It's just like multiplying by the conjugate. We've seen these sort of tricks in taking limits before, just not with trig functions, usually with square roots. But when I multiply these across, upstairs, something nice will happen. I'll have cos h times cos h, which is cos squared h. And then plus cos h minus cos h, those will cancel. So I have cos squared h minus 1 all over h times cos h plus 1. And cos squared h minus 1, say recall, sine squared whatever h plus cos squared h. That's definitely 1. That's your Pythagorean identity. So if I subtract the 1 over, I'll get sine squared h plus cos squared h minus 1 equals 0. And then I can subtract the sine squared over. So I'll get cos squared h minus 1 equals negative sine squared h. So this numerator, cos squared h minus 1, is negative sine squared. This is lim h to 0, negative sine squared h over h times cos h plus 1. Pretty sneaky algebra, or trigonometry if you want. Now I'm going to group terms here. So the negative I'm not too worried about. This is lim h to 0. I've got, I'll write the negative term out here. How about negative sine of h times sine of h over h times 1 over cos of h plus 1. So check for yourselves or verify algebraically that this is a kosher split. I've got sine h times sine h upstairs. I can grab off a sine h and I'll group that with the negative. Then I've got one more sine h upstairs. I'll group that with the h from downstairs. And then I've got cos h plus 1 downstairs. So if you multiply these three fractions, right, thinking of this first guy as this over 1, then you'll get the thing we started with, or the thing we had in the line above. It's nice to group them like this because these pieces are easy to take limits of. So I can use my limit laws and say, okay, this is the limit as h goes to 0 of negative sine h times the limit as h goes to 0 sine h over h times the limit as h goes to 0, 1 over cos h plus 1. This piece is the negative sine of 0. Sine on its own is continuous, so I can just plug in. This piece is 1. That's my special trig limit. Sine h over h goes to 1 as h goes to 0. This piece is 1 over cos 0 plus 1. So what are those? Well, the sine of 0 is 0. 1 is 1. What's the cosine of 0?
Isn't it 1?
Yeah. So this piece is 1/2. So I have 0 times 1 times 1/2. That's 0. So as promised, the limit as h goes to 0, cos h minus 1 over h, that is indeed 0. So L1 is 0, right? This was the limit we called L1. And L2 is 1, which means that the derivative of the sine function is the cosine function. I know that this last piece is 1/2 because the cosine of 0 here is 1. So I have 1 over 1 plus 1. 1 plus 1 is 2. So that's 1 over 2, or 1/2. Yeah, so we're looking just at this piece. Downstairs here is 1 plus 1 because cos 0 is 1. That's all. Nothing fancy that. I recognize this is a fairly complicated argument. So I'm going to come back and summarize things for you guys. But I do want you to take a second, make sure you're following the processes. Questions about what we did here? Okay, I'll hold here for about 5 more seconds. You can take a screenshot if you need one.
So we won't need to do that. We just need to know that cosine squared h minus 1 over h is 0.
I'll summarize the things I'm expecting you guys to take away from this. L1 and L2, we're going to call these special trig limits. I do expect you guys to remember that this limit is 0 and that this limit, sine h over h, is 1. And you should be able to work with those things in this sort of fashion. But I'm not going to ask you to reproduce this exact argument, and I'm definitely not going to ask you to reproduce the geometric argument for sine h over h.
So as long as we see that like sine h over h in the equation, won't it always end up 0 because you're multiplying 0 to everything else?
This piece right here goes to 1.
Oh, 1, never mind.
And we need the limit. So without limit h to 0, this wouldn't be necessarily going to 1. So yeah, we do need to remember that the limit as h goes to 0 of sine h over h is 1. That's something I would ask you guys to remember. And I do need you to remember that the limit as h goes to 0 in cos h minus 1 over h is 0. So let's get back here. Let's get back to where we were here, which was this.
Professor, I have a quick question.
Yeah.
Since we know that sine of h over h is 1, isn't it reasonable to infer that sine of h minus 1 over h is going to be 0 then as well?
Not necessarily. If you subtracted 1 from this whole thing, yes. But if you subtract 1 in the numerator, no.
Okay.
Yeah, that if you just subtracted 1 in the numerator, then this would actually become unbounded rather than going to 0. This would go off to like negative infinity from one way and positive infinity from another way. But if you were to say sine h over h, and then outside of that fraction minus 1, send h to 0, in that you could infer that that limit is 0. But remember here, the thing we're looking at is cos h, right? This is a cosine, not a sine. So the one doesn't come from the other quite that quickly, but it does come from the other guy. All right. So what do we have here? Since this first guy is 0, and that second guy is 1, I get 0 times sine of x plus 1 times cos of x. This is where we were in our calculation. And that is just cos of x. So if f of x is sine of x, then f primed of x is cos of x. That's what we've learned here. In other words, the derivative of sine is cosine. i.e., well, this can be otherwise written dx of sine x equals cos x. And this is something you really want to hold on to. A very similar argument, right, going through the exact same sort of stuff. Will show that d dx of cos x is negative sine of x. And this you must also hold on to. So the derivative of sine is cosine, and the derivative of cosine is negative sine. The two special limits that you need to remember from this section I'll call them special trig limits. We cooked up. And you must remember for this are lim h to 0 sine h over h equals 1 and lim h to 0 cos h minus 1 over h, this is equal to 0. All right. So these are the things that I need you guys to take home from the lecture so far. These are the things I need you guys to hold on to. There are a handful of trig limits in your homework this week that require you to use these guys kind of as your starting point. And then of course, there's a shitload of problems that require you to use these facts, right? Most of the homework this week is differentiating trig functions. I'd like to show you a few examples of each of those. And one of the best sort of examples I can work with you at this point is getting the derivatives of the other trig functions from these using product and quotient rules. So I'll do one or two of those and then one or two of these special limit type arguments so you can get a feel for how those work. I'll say one more time, this is the really important stuff from this section. These are the things that you need to remember. So make sure this gets in your notes nice and clean, maybe take a screenshot, whatever. In about 5 seconds, I will switch to doing example problems. Okay. So what about derivatives of other trig functions? If I really wanted to torment you, I could sit down with the tangent function, blow it up using an addition formula, and then reduce it down to special trig limits. Sorry, my wife texted me. But that would be torture, that would be hell, and there's absolutely no reason to do it. So let's not do that. I'll tell you, you need to know the derivative of all 6 trig functions. I'm going to cook up the derivative of tangent here as an example, but then at the end, I'm going to, put it in a box and we're going to say this is holy and we're going to remember this just like we're always going to remember sine and cosine. How could I possibly do this? I know the derivative of sine and I know the derivative of cosine. How can I
Did you
use that?
rewrite tangent into terms of sine and cosine and then use the quotient rule?
Perfect. You know that tangent, tan of x is sine of x over cos of x. I'm going to say this once. Please always write the inside of your trig functions. If I see just sine over cos with no x inside, I'm going to take off points. This is important. All right, the x's, for one, don't cancel, and there's no way to algebraically maneuver them from inside the trig function to out. But more importantly, later in the semester, the variable that you're using inside there might be different than variables that are showing up elsewhere in the problem, and it is super important that you always write the inside of your trig functions. Don't get sloppy. But Adrian's suggestion was perfect. We're going to rewrite tangent as sine over cosine, and then use the quotient rule. The quotient rule says we take the bottom times the derivative of the top. So I'll write this out kind of schematically. This is going to be cos x times the derivative of sine x minus the top, which is sine x times the derivative of the bottom. And we divide all of that by the bottom squared. Now, what are these pieces? Well, this is cos x times the derivative of sine. What's the derivative of sine?
Cosine?
Cosine. So that first duo here is cosine x times cosine x minus sine x times the derivative of cosine. What's the derivative of cosine?
Negative sine.
Negative sine.
Yeah, good, negative sine x. And these parentheses I'm writing here help me see that these are being multiplied, right? Not being subtracted. If I didn't write these, this would look like more subtraction. So please use the parens. And then downstairs, cos x times cos x is cos squared x. Can I cancel the cosines?
Yes.
No, because there's terms on top and factor at the bottom.
Yeah, these guys over here don't have a cosine in them. You can only cancel that which you can factor from the top and the bottom. I can't factor a cosine out of the top because there are no cosines over here. So I cannot cancel those. As tempting as it may be, I cannot cancel those. But upstairs here, cos x times cos x, that's cos squared x minus sine times negative sine, that's plus sine squared x. So this is cos squared x plus sine squared x over cos squared x. Still can't cancel these because I can't factor cosine out from the top. You can only cancel if your immediate step before was factoring. And you cannot factor a cosine out from here. But what is cos squared plus sine squared?
1.
Yeah, that's my Pythagorean identity. So this is 1 over cos squared x. This piece right here is 1 by the Pythagorean identity. And 1 over cos squared, that's called secant squared. Right, because secant is 1 over cosine. Assuming there. All right. So what have we discovered? The derivative of the tangent function d dx of tan x is secant squared. Secant squared of x. You have in your homework for this week cooking up the derivative of the cosecant function, following this exact same sort of thing, right? Using the quotient rule, which means you will be doing cosecant. I've given you sine, cosine, and tangent. The remaining ones we need to look at are secant itself and cotangent. Any questions on this?
Isn't that have to do with the one of the identities too? Kind of, or no? The last part where tan x is equal to secant squared.
So careful here. I'm not saying tan x is equal to that. I'm saying the derivative of tan x is equal to secant squared. It's true that there is a Pythagorean identity linking tangent and secant, but that's independent of this statement. So here we're saying not that tangent is equal to this or tan squared or anything, but that the derivative of tangent is secant squared. Secant squared happens to be the same as tan squared plus 1. So you could say that tangent's derivative is equal to tangent squared plus 1. And that's what's called a differential equation. And there is a possibility of defining the tangent function as a solution to that differential equation. But I would say that this is a totally separate thing, although it's similar looking. I agree. You've got tangents and secants, you've got squares. But this is not the same as the tan squared plus 1 equals secant squared identity.
All right, thank you.
Yeah, good question, though. Fair question. All right. So far, we know how to differentiate sine and cosine. We know how to differentiate tangent. I'm going to give you secant. Same sort of thing. Secant of x is the reciprocal of cos x. That's just the definition of secant. So I will apply the quotient rule. That is the bottom times the derivative of the top. So this is cos x times the derivative of 1 minus the top, which is 1 times the derivative of the bottom, all divided by the square of the bottom. The derivative of 1 is 0. So this is the same as cosine of x times 0 minus 1 times the derivative of cos x is negative sine of x, all divided by cos squared. We can think of these as being in parentheses if we want, like this. Anything times 0 is 0. So this piece right here is 0. And then I've got minus negative sine. That's going to become plus sine. So I'll have sine x over cos squared of x. Now I can rewrite that as 1 over cos x times sine x over cos x, which is secant x times tangent x. So the derivative of secant is secant tangent. The way I remember this is that secant is the fella who shows up in his own derivative. So I had sine x over cos squared x. This is the same as sine x over cos x times cos x. So I can just split this up if I want to as sine over cosine and 1 over cosine. If you multiply these two fractions straight across, you get 1 times sine over cosine times cosine, which is sine x over cos x times cos x, which is what we had here. So I just chose to pull one of these cosines off and write it as 1 over cosine because I was asked to find the derivative of secant. I would like to write it as nicely as I possibly can. So when I look at sine over cosine squared, I'm asking, you know, how can I write those as individual trig functions rather than as a fraction of trig functions? I know that sine over cosine is tangent, but if I just grab sine over cosine out of this, I have an extra cosine downstairs. So I've got sine over cosine times 1 over cosine. And then each of these I'm able to rewrite as secant and tangent respectively. So just using some basic algebra stuff like a over b times c is the same as 1 over b times a over c. In general, we can always do this sort of thing, like a over b is always the same as a times 1 over b, because a is the same as a over 1. So it's kind of some clever algebra, and it's not the sort of algebra we use to solve equations a lot, so it might not be something you've seen a lot, but I promise it is consistent with the algebra you use to solve equations. All right, so we've got sine, cosine, secant, and tangent. We know how to differentiate those, and those are your 4 main guys. Remaining are cosecant and cotangent. I think rather than going through the argument for cotangent, which is exactly the same as the argument for tangent, I'll just tell you also the derivative of cotangent x, this guy is negative cosecant squared x. It's literally the same thing we did for tangent. So the only one that's missing now is cosecant, and that one's in the homework for you guys to do. So I don't want to spoil it. I'll tell you kind of similar to how, you know, tangent had derivative secant squared, cotangent has derivative negative cosecant squared. Secant has derivative secant tangent, so cosecant will probably have a negative, probably a cosecant, and probably a cotangent. But I would like you guys to work that out on your own. And those will be all 6 trig derivatives. So before we go, I want to do one more example here, where we're putting together product rules and trig derivatives to do something fun. And I'll tell you that this is also in your homework. So questions on this page before I scoot? Okay. So one last example for today. Let's find the equation of the tangent line to f of x equals x squared sine x at x equals pi over 3. As always, I need two things. I need a point and I need a slope. My point is going to be pi over 3 comma something, but I need to figure out what the something is. So what is f of pi over 3 here? What's the point on the graph where x is equal to pi over 3? It's pi over 3 squared times the sine of pi over 3. Pi over 3 squared is pi squared over 9. What's the sine of pi over 3? What's this piece? Who remembers their unit circle? Ooh, you guys are scaring me a little bit here. All right, so in parting, since this is clearly something we need to do, I want to remind you, I have resources for you to help remember your unit circle. If you didn't remember it, I'm not going to judge you. I don't know whether you learned it and forgot it or you never learned it, and I'm not going to judge you either way, but your unit circle. Oh shit, is it not in here? All right, here, let me make a note. Another one. Is it left-handed? It is, yeah, left-handed. All right. I will put links to these in the modules. Sorry, I have them there for my pre-calculus classes. Sine of pi over 3 is root 3 over 2. So this is pi squared times the square root of 3 over 18. So that's my point. The slope is the fun part here, right? I want to take the derivative. This is going to be f primed of pi over 3. And in order to get that, I first need to find f primed of x. So how do I differentiate this function, x squared times sine of x? Someone help me with this derivative. What rule do I need here?
The product rule?
Yeah. So don't worry too much about what it's all going to simplify to. Let's just write it out. I differentiate the first piece, leaving the second piece alone. And then I add that to what I get, leaving the first piece alone and differentiating the second piece. Right? So like f prime times g plus f times g primed. The derivative of x squared is 2x. So that first bit is 2x sine x plus x squared times the derivative of sine x. What's the derivative of sine x?
Cosine x?
Yeah. All right. So this is f primed of x. So what is f primed of pi over 3? Well, again, we're going to have to know our unit circle. This is going to be 2 times pi over 3 times the sine of pi over 3 plus pi over 3 squared times the cosine of pi over 3. 2 times pi over 3 is just 2 pi over 3. What's the sine of pi over 3? We used this earlier.
Square root of 3 over 2.
Good. Plus, now I have pi squared over 9 times the cosine of pi over 3. What is the cosine of pi over 3?
1/2.
Yeah, good, 1/2. This is a pretty gnarly looking slope, but we can still work with it. This is 2 pi square roots of 3 over 3 times 2 is 6 plus pi squared over 18. All right, that's my slope. So if I want to put all of this into my tangent line, I use the same point slope formula, right? Y minus y0 equals m times x minus x0. My point x0, y0 is pi over 3 comma pi squared root 3 over 18. And my slope m is this whole expression here. So this is going to be y minus pi squared root 3 over 18 equals m, which is this slope. I'm not even trying to simplify it. I'm just going to leave it. I'm sure we could simplify it a little bit if we wanted to. So here's my m, and then x minus pi over 3. That's it. That's your tangent line. This piece right here is m. This piece right here is y0. This piece right here is x0. So this really is y minus y0 equals m times x minus x0. It's just that these pieces are a little bit scary looking. I made this guy up. All right, I didn't think ahead too hard to make sure these numbers would come out nice. Your operations in the homework will, for the most part, yield more pleasant looking numbers than these. But this procedure right here, coming up with your derivative, very, very important. This is the main thing we're worried about. So next time, we're going to get lots more practice with these, right? I'll solve a handful of homework problems for you guys and a bunch of other derivatives involving trig functions using the product rule and the quotient rule. And also we will introduce the chain rule. The chain rule is a tricky biscuit. So your homework this week is split up into 2 primary parts. One is all about derivatives of trig functions and combinations of those using product and quotient rules. The other part is all about the chain rule. The chain rule problems you're not ready for yet. We haven't talked about those. But I will talk about those starting on Wednesday. And then I think by Friday, we will finish all of the chain rule stuff, which means that exam 1 is going to be a week from this Friday, I think. So you can take a healthy bet on that. We might finish it a little bit sooner. Let's see where we're at here. So exam 1 will either be the 10th or the 12th. I think might be best to shoot for the 10th. What did we have in the syllabus? I think it's supposed to be around here. Exam 1 to 25. Yeah, so we don't want to push back any further than we have to. So let's say exam 1, we'll go ahead and set the date now. Exam 1 is going to be on the 10th. And I will release the study guide after we finish our lecture on the chain rule, which will be this Wednesday. Friday will be more practice with the chain rule. Monday will be review. And then Wednesday the 10th will be exam 1. finish up with this little note. Next time, chain rule. And then exam 1 will be Wednesday, 2:10. Study guide 1. I will release this week on Wednesday, which is the 3rd, right? Yeah. And it's due at the start of the exam. But I strongly encourage you, and I'll talk about this a little bit more next time, to take these study guide problems and submit whatever you have done a little bit early. So you can email them to me, you can submit them. If you finish the whole thing, you can submit it in Canvas whenever you want before the exam. But the sooner you can share your work on these study guide problems with me, the sooner I can get you feedback that will help you on the test. You can bring them to office hours. You can email me pictures. You can do whatever you want. But the point of the study guide is for you to write out your solutions and share them with me before the test so that I can give you some feedback and pretend like these were test problems, show you where I would have taken off points or where I would have given you full credit. And that way you'll not be surprised by any of the grading on the test. Any questions before we go? Alrighty then, I gotta get running. I hope you guys have a good rest of your day. Homework 5 should be up by now, so you should be seeing that available. If not right now, then within just a few minutes. Take care.